Mhm. So hello. Can you guys hear me?
Yep, we can hear you.
Uh, uh, so can you guys hear me, or is everything good? And can you guys see the screen, the slides?
We can hear you and we can see the slides.
Yep.
Uh, mm, yeah. Okay. Thank you, David. Uh, so so let's get started. So this is kind of like an introduction. Uh, uh, to the so this is an introduction to the graph database. Using hopefully you guys already download, not really download, but register this Neo4j sandbox so that you can do some. We will do some like in class practice. Write some basically queries that using a language called Cypher. So just briefly review what's the database is. It's kind of like the database contains three levels conceptually. So on the very top, there's an external level, which basically application view. For instance, one application could be social networks. But in order to like support this social networks, and we kinds of data models to support social networks. So we can, for instance, implement social networks using graph models, or implement social networks using a relational model, or etc. Furthermore, at the very bottom, we can implement those like logic models using different kinds of physical implementations. For example, we can implement graph model using, say, store graph natively using like say adjacency list, or adjacency matrix, or edge list, and etc. Or we can implement a graph model using, store graph as a collection of key value pairs, where key is vertex and value is the vertex neighbors. Um, so the history of a database is kind of like it starts from uh, around 70s, and at that time there not really there are kinds of like lots of different data models. So in the class, hey, uh, mostly focus on the relational model, but as you can see here, we have different kinds of models like hierarchy model or network model. But today, but eventually, a relational model becomes the most popular one. However, today we're gonna talk about graph databases, and graph databases using data models that's a kind of like successor of this network models that's really popular in the 70s, but start to die down a little bit. But now the interest to that model, or refinement to that model, yeah, becomes a popular again. So we are really so I briefly introduced two graph models here. The first graph model is edge labeled graph. We are not going to talk about this in extensively, but you will see how this idea is going to be used in the second model. So the edge labeled graph, which essentially says that we can assign labels to edges that indicate the different type of relationships between nodes. So in this case, I use this running example that contains three nodes and three edges, which essentially models a TV show called The Office. So we have the three nodes, which is Steve Carl, the office, and the BJ Novak. And we have three edges, which for instance, Steve Carl, this edge axing means that Steve Carl acts in the office, which he plays a role in the office. And similarly, BJ Novak also acts in the office, and also BJ Novak produces the office. So the nodes we'll see is has in this graph has three nodes, and we also have three edges. To indicate this edge, for instance, Steve Carl acts in the office. Essentially, we represent it using three components. One is that the three components, for instance, in this case, we have two endpoints. One is Steve Carl and the other is the office. And we have a label, which is axing. So we have three edges and we have three, as you can see here, we have three, the three elements in this edge set. So this graph model is usually it's called Resource Description Framework or RDF. And it's also nicknamed Triple Store essentially because the edge has three components in it. The second graph model, which is called the property graph model, which we'll talk about more today. So the property graph model essentially extends the previous edge label graph with labels. So that means that both edges and nodes can be labeled with a set of property value pairs called attribute directly attached to each edge or node. So in this case, still we have the same exactly identical example. We have in this graph we have three nodes and we have three edges. So nodes in this case have a node label. In this case we have essentially two labels. One is a person, and two nodes have the label person, and one node has a label TV show. And edge also has edge labels, which has a label X in, and it has it can be arbitrary number of key value pairs. In this case, both so for instance, in this case, we have two edges, two axing edges. We have two key value pairs. The first one is the row, the key is row, and the corresponding value is Michael G. Scott. And second is the reference, and the value is Wikipedia. Of course, we don't really not every edge or node can need to have these attributes. For instance, in this case, the edge E2 here only has a label which is produced, but it doesn't has any attributes. So let's just briefly compare these two graph models. So having node labels as part of the model can offer a more direct abstraction that is easier for users to query and understand. So for instance, without really a semantic knowledge or meaning like trivial knowledge about this graph, one can imagine that one cannot really tell whether Steve Carl and BJ Novak are really a person. Even though it's kind of like trivial, we can directly see, I've judged by the name, this is Steve Carl, that's some person's name. BJ Novak is some person's name, so that we can tell that it is a person. But in other situations that we cannot really easily tell what we try to model here. The second advantage that property graph over the edge label graph is that it's more suitable for scenarios where various new types of meta information may regularly need to be added to edges or nodes. Remember the previous we saw that every node or edge can have an arbitrary number of key value pairs. So we can easily add extra key value pair to the node or edges without really modifying the structure of the graph. However, if we see this one, if we want to add, say, some extra information, we may need to kind of like change the graph structure a lot because we don't really have much freedom about adding extra things to each individual node. So let's compare a little bit on the graph versus our traditional relation model. So it's usually the one nice thing about graph is that it's called this schema extensibility. So consider in this case, we want to model the exactly same graph using relational model. So we basically saying, okay, we want to first create table called TV show that has title year, and then we want to create table production company that has name and executive producer. So essentially we have some graph like this. Now, so then basically we in order to link these things together. So essentially, we need to kind of like have this foreign key references, so that we can like create some connections between these two tables. So usually that is very intuitive if we want to say we have two graphs that we directly want to connect these two components, we can just directly add an edge. However, in the SQL, we basically we need to kind of we need to redefine the relational schema by change our schema using alter table, saying that, oh, in this case, we want to adding instead of just TV show title year, we will need to add a foreign key constraints that links between TV show and the production company. So just to give a more concrete ideas about how we can model exactly the same graph using relational model, here we can basically say, okay, here's exactly the graph, but actually we implement it using relational model. So here we have essentially 1, 2, 3, 4 tables, and we have a foreign keys in order to link those tables together. And we also need to add in some IDs so that we can know which row linked to which row. But usually those things, if we consider from the graph model perspective, those IDs are usually you don't see those IDs. So let's just briefly summarize what we have talked about so far on the property graph versus relational model difference. So the first point is that property graph its graph structure is more intuitive than a collection of tables. As we will see in this class, we'll talk about how we can implement an organization chart using graphs. Usually the ambiguity in graph representation using relational model. So usually that means that like I think I forgot whether we have I don't think we have done the homework or not. So usually when you're using the relational model to implement a graph, you cannot really tell whether we are implementing a directed graph or undirected graph. Usually you have to actually see the content of the table. So for instance, if I have an edge table, we have two columns A, B, and if we have say the two values 1, 4 and 4, 1, that usually means that we are implementing a directed graph. If we only have say 1, 4, and we cannot really tell whether that's directed or undirected. It could be directed or undirected. And as we saw earlier, that the relational models has repetitive data storage from user perspective. So essentially, because we need to use a primary key and foreign key to establish the connections among tables, we want to assign IDs to each individual rows. But those information it's really for the sake of implement a graph using relational model. It doesn't really do anything with our data itself. As we saw earlier, that actually the relational name the node can have the same label. Say in the previous example, we have person. We have two nodes has a person has the same two nodes have the same label person. However, in this case, in the relational model, we cannot really have the same schema, within the same database. So in this case, if we want to create table, TV show, title, year, that's fine. But if we do this again, create table, TV show, title, year, and then we say production company, that's really not possible because the TV show already being used. So we have to figure out a different name. And this is more like, it's more a subjective point of view. This is usually when coming to query graphs, using graph native query language is usually much easier than the SQL for on the relational model. We'll see an example later. So, so data modeling in this case, it seems that maybe we talk really about a lot about data modeling. So data modeling is still quite relevant in graph case as well. So, so we can say, so for instance, for this example graph, we can have exactly the same. We can have using different kinds of models, but we still need to using sort of like modeling technique to model it, even though, but you can see the model is quite close to the data we have compared to relational model. So today we're gonna really talk about graph model in a more concrete sense using a database offering called Neo4j. So Neo4j is a graph database that uses property graph data model with a query language called Cypher. In graph database domain, so that's probably gonna be this is a lie because as we'll see that quite recently that we do have standard query language, but that this statement may also be true because the support on that standard has not been matured yet. Compared to many databases support SQL. So we have this many vendor dependent flavors. Say there's a language called Sparkle that is for RDF, and the Cypher, Grammarly, and etc. for property graph. So we'll see one example here. So in this case, I just showcase 3 different languages using implement the exactly identical query, which is find the co-stars of the office. So this is Sparkle, and this is the Cypher, and this is Grammarly. We don't really talk this too much, just to focus on this kind of like a language called Cypher. But just please do remember that these 3 languages are both kind of like equally popular. So even though we focus on this one, that doesn't really mean that you won't see this too in your real life scenario. So I just here I just list a bunch of query languages, as you can see on so basically the first row and third row basically is the different kinds of graph products that's are available in today's market, and the third and all this even numbered rows that represent the language those graph product use. So just kind of like saying one more thing about this standard graph query language. So we essentially have 2 graph language. One is called GQN and GQN, and the second is called SQL PGQ. So this is actually the timeline. So each year, I kind of talk about this. This timeline is kind of like initially this is where we are at right now. So this is almost like at the beginning of Q2 of 2024. So last year we have this SQL PGQ release, and this year I think we have GQL already is released. So what does this 2 language do? So the first one is a GQL. It's completely new language for graph databases. So it's nothing to do with SQL. And second is that SQL PGQ is essentially extending SQL with graph query capabilities like path finding, pattern matching, and etc. So basically, this is kind of like this support 2 kinds of scenarios. One is that you want to build your companies, and then you decide to build everything from scratch, and you decide to use a graph database, and you decide to write all your analytics tasks using a completely new language, GQL. You don't really have any legacy code at all. So this is the GQL case. And SQL PGQ is that you are running a kind of like mature company. You have lots of analytics tasks running in your pipeline, and they are all written in SQL. But however, one day you want to extend your analytics task with some graph data and the graph support, but you don't really want to rewrite everything, in GQL. So in that case, you want to extend existing your SQL task with extra features to support your graph data. In this case, you use SQL PGQ. So, but essentially, you see that actually the GQL and the PGQ, this all the components related to graphs, they are compatible. Essentially the same, but we'll see example at the very end. So let's dive into the poverty graph and the Neo4j and the Cypher. So in this case, we create this office crew graph, which has been our running example so far. So how can we create this graph using Cypher in Neo4j? So this is the statement. So we first with create, and we have essentially we have 3 nodes and 3 edges. So here the first one is N1, which correspond to this node N1. So this is identifier, and we have a person, and then we have a name. This person is the label of the node, and we have this 2 attributes: name Steve Carl and gender male. Similarly, we create our N2 node and we create our N3 node. And in order to create edges, we can just effectively draw the edge. So using the information we have written out so far. So in this case, we want to create this E1 edge. So we have this N1 node, which N1 identify the first node we have here, and then we create an edge, and then we link that to the N2 node. And for the edge, so here we have again we have this label X in, and we have several key value pairs, so-called attributes. So first one is row, Michael G. Scott, and reference Wikipedia, and N2. So so one thing to note here is that in the Cypher, the Cypher assumes that the graph is directed. So in this case, whenever we create an edge, it's always directed. But when you do query, you can intentionally ignore the directions of edges. So let's do a little bit practice. So in this case, in this class, we're gonna create the organization chart of the paper company Dunder Mifflin Scranton branch in the office. So just to make our life a little bit easier, just all the edges will have labels, EI managers, with I being numbered from 1 to N. So there are some useful commands and notes. So in this case, we have so if you in the sandbox, if you want to see the graph, you can run this command match n return n limit 50. That's more than enough for our graph. And if you want to delete the whole graph together, you can say match n detach delete n. And in some cases, the nodes we can have this. Remember the key value pair, the value not necessarily being a string, it can be a list. So in order to create a list, for example, we have a row which is sales and say some person. In this case, we have this key row and we have a list. One is sales and the other is assistant regional manager. We can use the angle brackets. Okay, so maybe we can spend like 5 minutes to just play around in the sandbox for a bit. Yeah, let me know if you have any questions. Hopefully I don't. Okay. There's one question in the chat. So we should start with the blank. Yeah, yes. So yeah, correct. No data in it. I don't have access to my computer to using the. So is there that I'll be able to find the after the find slides and recording after lecture. Yes. So for the sorry. So for the slides, yes. It's already in the box, and I'll share the recording later. Okay. So so in case you didn't really notice, there's basically all the Cypher commands or Cypher language statements that we talk about today, even about this create this organization chart, is available in the box folder from last year. There's a subdirectory called graph database lecture, and there's a bunch of Cypher Cypher files there. You will see how you can see how. So maybe let me just maybe show you guys this. So yeah, so here in our box, we have this uh, so we have this lecture notes 2023, and we have introduction to graph database with Neo4j. So in this case, you can click on this one. Probably it won't allow. I'm not sure, but this file will contains all the will contain the Cypher queries just for this organization chart, and this one will contains several others queries we're gonna talk about today. Okay. Uh, so we have this graph query languages. So there are two important usage patterns for our graph query languages. One is called graph pattern matching, and the other is called graph navigation. So we'll focus on Cypher in this tutorial. However, any significant graph query languages will have these two important patterns in their languages. So the first one we'll talk about graph pattern matching. Graph pattern matching. Essentially, we define a match. Match is a mapping from variables to constants, such that when the mapping is applied to the given pattern, the result is, roughly speaking, contained within the original graph, or also called subgraph. So let's just see one example. Suppose we have this again. We have this uh, office crew graph, our running example, and we want to the first query is that we want to find co-stars of the office, and we can actually model this query using graph as well. So the graph pattern of this query, which essentially look like this. So we have a TV show which has a title The Office, and we want to match any arbitrary nodes in our original graph, such that the node x1 will be a person and it has a label person, and x2 node will also have label person. But we don't really impose any constraints on what is exactly inside inside the attributes inside each node. But we also constrain that for this x1 node, it has to connect with this n2 node with a edge has a label x in. We don't really care what exactly the attributes within this edge. And similarly, we want to also have this x2 node connect with this n2 with an edge x in. And also remember, we have this constraint about these directions as well. So once we're using this graph pattern to match to find whether what kind of essentially what node we can bind this x1 to, and what node we can bind this x2 to, we can see there we got two results. One is that we can say x1 be Steve Carl, and then x2 being BJ Novak. However, we can do this by flip this like graph results by binding this x1 to BJ Novak and x2 to Steve Carl. And usually the result set is kind of like a name for relational or SQL, and in this case, in graph we call this matching. So matching for Q1 can be two pairs in this case. So how can we write? Essentially, here we illustrate that we see how we can conceptually represent our query using graphs and then perform this query, essentially this query evaluation on this graph. How can we actually write this graph pattern in Cypher? So Cypher has no repeated edges, back semantics. The details doesn't not really our concern for this class today. So we mostly focus on the examples. So suppose we have this our Q1, which is find co-stars of the office, and conceptually we have this graph. And to represent this graph using Cypher, we have this we can write this statement. So first one is that we have this keyword called match, indicate that we want to write essentially a query. So if you remember in when we create the graph, we don't really have this keyword. And then we have this x1, which identical to how we create how we create this graph. So we use this parentheses indicate that it is a node, and we use angle brackets to indicate the edge. It's exactly the same in the with the graph creation case. So here we have this x1 person, and then that means that we want to match variable x1 to node with the node label person. And here we have this again we have this TV show node, and we have this edge label x in. So in this case we are saying that x1 has to connect to the TV show, x1 has to connect to TV show nodes through an incoming edge with edge label x in. So we repeat the exactly same. As you can see here, we actually draw this directions of edge identical to what we see here in the graph. So maybe let's practice a little bit, just maybe spend like 2 minutes to think about how we can write these two queries based on the organization chart. If you really want to see the answers, you can look into the box and to the Cypher file to see how these two query get write out. But we'll talk about it in 2 minutes. Oh, shoot. Okay, so let's take a look at these two queries. So first one is that who's inside party planning committee, PPC. So in this case, the hint is PPC is a department that essentially the PPC is a node with a label department. So this was so here we have our match query match P, which P is some variable, arbitrary variable P, and is some with a label person. So that indicates all the nodes with a label person. And this is our familiar where clause indicate that party planning committee is inside this P dot depth. So P dot depth is uh excuse me. So actually, P dot depth. Actually, that means that essentially that means this party planning committee. Essentially, in this case, this is attribute key. So not really an so essentially we are saying that this party planning committee has to be part of the value inside this P node. Uh, and then we return p dot name, which basically we return p dot name. And the name here again is a key of the attribute. So basically, we want to find out all the corresponding values, and we want to find basically all the node. So essentially, this query says that we want to find all the nodes that has attribute depth and its corresponding value is party planning committee, and we want to find out the corresponding. We want to return corresponding value of the name key. And the corresponding means that all this nodes with label person. For the second query, how many people does Michael directly manage? So in this case, we write out a little bit graph pattern here. So we have this P, which some nodes with label person, and we have some N also being a person, and we have this H managers. And we want to say that actually the n dot name equal to Michael Scott. And we're using there's a built-in function called count. Essentially, we count how many patterns we have here. So then we just directly return count P. Okay, so wait. So let's just take a further look at this two queries directly. It's a little bit more complicated than the previous two. So the first one is that we want to find all the employees that are directly managed by someone that reports to Michael. So here, actually, this shows that we don't really necessarily need to use this where pattern to specify the attribute values or constraints on the nodes. We can directly say them inside our match pattern here. So we can say here the P, and then it has a one attribute called name, and the corresponding value is Michael Scott, and then it manages and then we say some Q, and then we return Q dot name. Since Q here in our graph, we only have a person, so we don't really need to specify the label name at all. We can just say some Q, and then Q has to be some node. And then in this case, also in this query, we have this empty parenthesis. That means that it really means that we don't really care exactly as long as it's some nodes. So basically, it says that this pattern says that this P, which is Michael Scott, actually manages somebody, and that somebody manages a Q, and then we return Q dot name. And for the second query, does Michael directly manage more employees than Jim Halbert? So here this query actually shows how we can specify multiple patterns within the same query. So in this case, we have two patterns. The first one is match P person and manages N person. Notice this graph, this H directions is to the left, and then N has to be Michael Scott, and then we use this with count P as C1, basically saying that how many patterns we can find using the first pattern here. And then we write our second match. So here, second match says that we P person and manages M person, and then where M dot name equals to Jim Halbert. And then we just say, okay, we want to return whether C1 is greater than count P, which is count number of patterns for this second match. So so each match where can be sought as a select from where in the SQL. So we essentially have two select from where within this Cypher query. And you can play around with this to just kind of see what's going to happen if you don't really have this with class and how different these two queries going to look like. The second pattern we're going to introduce today, which is called graph navigation. So it's a mechanism provided by graph query languages to navigate the topology of the data. So two important query classes. One is called path query, and the second is path query plus graph pattern matching. It's also called navigational graph pattern. So let's start with path query. So previously we matched a graph pattern. Now we want to match a path pattern. So path query has the general form of p equal to x goes to y with a label alpha, where alpha specifies conditions on the path we wish to retrieve, and x and y are the endpoints of the path. So usually these conditions are represented using regular expressions conceptually and in most cases languages. So in this case, we have this, again, our running example, the office crew graph, and we want to, again, find the co-stars of the office. So here the want to find the co-stars of the office, instead of finding we want to find a pattern, we want to find all possible paths. That means that how we can go from one node to the other node that satisfy this query intention. So conceptually, if we want to represent this query, we can say that is p equal to x goes to y, and we have two edges. One is x in, and then then we have this dot, which is concatenation operator that we want to have this concatenate. So basically x goes to x in and then goes to x in reverse. So this minus sign indicates that h has a direction. But that's not really that. But that's, remember, that is how we represent this query conceptually, not really how we want to write it out. So if we want to write it out in Cypher, actually it's almost identical to the graph pattern matching. Is the only exception is this path equal to, and there's really nothing new here. Is that because the rest of the pattern is exactly identical in the case of graph pattern matching we have talked about, but the only difference is this: we prepend this match pattern with a variable name, in this case path, equal to this. But the return, as you can see, the return here will be a little bit different. So instead of saying that what exactly this P or Q gonna bind to, so here we actually return a full path that's basically on the graph that we can navigate from P goes to TV show, and then Q goes to TV show. So if you can see here, the first one, P, is Steve Carell, and then it goes through this office node, and then this Q is BJ Novak, and we have the mirror case on the second row. So navigational graph pattern essentially is that we can combine the path query with graph pattern matching by allowing edge labels in the graph pattern to be paths. So consider this query: find all the people that Michael Scott manages. So in this case, we have conceptually we have this two nodes. N1 person, which is Michael Scott, and then we have some person which is X1. We want to find out what exactly those persons are, and then we have this managers. You notice this plus sign that's in the regular expression. That means that one or more, meaning that there could be at least one person, at least one edge manages that goes from Michael Scott to person. So in order to represent this graph, it represents this query using Neo4j. Using Cypher, we can write this match path equal to P person, and then it goes to the Q person, and it goes to about multiple edges. So here we have this edge label manages, and we have this star one dot dot. That means that we have this, at least we have to have at least one edge that goes from P to Q. It can be a multiple if there's a path. So let's see some examples here. So the first one is that get the Dunder Mifflin employees that are on the same level as Michael Scott. So essentially we have two match patterns here because we on the same level you should translate that into a query. That means that essentially there are multiple paths from Michael Scott, and the path length has to be the same. So the first one is P1, which has n person manages sorry, the P person, which P here is so it's n person, and then we manages P person, and then we have a second match with which is M person manages P person, and the length of these two paths has to be the same, and their N and M has to be the different. And one of the N name Michael Scott because we want to get the Dunder Mifflin employees on the same level as Michael Scott. So essentially, so there's some person P, and it goes to Michael Scott on uh, as a P1, and then there's again from the same person, it has to go to a different person M, but their pass length is the same. So maybe we can just showcase using this example to showcase how we can write this query using the SQL to kind of like make our point about concept subjectively that graph query may be maybe easier to use than the SQL. So actually this is the SQL corresponding SQL query is called recursion. So slides will be available. You can dive into details here just on the conceptual levels in order to write a recursion, because the recursion means that we want to have essentially we want to navigate a path and we want to repeat. Basically, we want to recursively following the edges to some node. So in this case, we have this base case is that if two people are at the same level, their manager has to be the same. And then we have our recursion step in the SQL that says that we essentially have the same idea as a base case, but we use the base relation and the result table we just computed in the base case. So that means that one recursion to conceptually we just traverse the graph by following edge once. So just for the sake of comparisons, this is SQL and this is the corresponding Cypher query, and they actually express the same meaning. So let's see a few more examples. So here, the first one is that Jim Halbert managed Phyllis Lapin. So that means that we are interested in whether there's a path exists that's between Jim Halbert and Phyllis Lapin that essentially we want to know whether this path is return result is empty or not. And you just notice that we don't really it doesn't necessarily has to be Jim Halbert directly matches Phyllis Lapin. It can be like there can be multiple like levels between these two people. And the second query is that we want to find all people that are indirectly managed by Michael Scott. So here we have this again P1 person Michael Scott is manages somebody, and then that somebody manages P2 person, and then we use this distinct to distinguish that all the paths we want to find out all this unique path. So one nice feature in the Cypher is that, or many existing graph query languages, that we can actually use in graph algorithms inside the query. So for instance, we want in this Q3, we want to find the shortest path between David Wallace and Andy Bernard. So in this case, we can directly invoke this procedure called shortest path, and then we can specify the pattern here. And actually, we can have more graph algorithms like PageRank, centrality, connected component algorithms, and etc. So like SQL, we can actually using the explain commands to understand the graph query languages. So so in this case, we focus on this natural join query, which is R1 join R2 and join R3. So if we run the explain command, we're gonna see something like that. This is essentially we have a you using the merge join. This plan is from Postgres. So we're using merge join, and then further then we have another merge join that join basically two merge joins to join the three relations. So to here, in order to so let's maybe model. So we present our data using the relational model. How we can map this into the graph model. So essentially, a row is a node. So in the relational model, a row is a node, and a table name is a label name. And attributes in relational schema become a properties associated with the nodes. And a join or foreign keys is a relationship, and that becomes a edge. So relationship means edge. They have the same name. The relationship, I think, is a Cypher term. So we can actually model this. We can create the graphs look like something below. And actually, so the only new things here is that we can, instead of directly specify, how we want to essentially draw the edges individually. We can directly write out this where clause so that we can say we can match any arbitrary node such that R1.b equal to R2.b, and then we can create create an edge. So that gives us like a convenient way to create lots of edges. So the resulting graph in Neo4j looks something like this. And in this case, again, if you notice that in the Neo4j, the edges always has a directions, always have direction. But we can ignore directions when we actually query the graph. And unlike the relational model, part of the join computation is done during the graph model creation. So in this case, that we actually, this edges we already created when we create the graph. So that in a way, this is more like a join. We already joined these two nodes together. So recall the semantics of semi-join. That's what we have done in the homework. That's A left semi-join B means that given a set of starting vertices in B, return the set of vertices in A that connect to those starting vertices via edges. So in the Cypher, for a multi-way join query, that usually means that a fixed length path query. So it means that say we want to natural join three relations. That means that we want to find all the paths that has a path length 3. So this is how we want to write in the Cypher query. If we actually see, if we want to run this explain command, just prepend this query with a keyword explain. This is the plan we're gonna. This is the plan we'll see. So here, if you look at this plan a little bit, so node. So first one is node by label scan. So that's kind of like a very intuitive name. We find all the nodes given to satisfy our constraints. The new thing is the second node, which is called expand all. So here it means that given a star node and depend on the pattern relationship, the expand all operator will traverse incoming or outgoing relationships. So essentially, it's equivalent to a breadth-wise expansion of the search tree. And then after this expand all with our third node, which is the filter. So means that after the expand all, we want to filter out all the unnecessary nodes or results. So in this case, the expand all plus filter implements our traditional join operation. So the execution starts with R1 and follows the edge from R1 by one more level to find all the R2s that satisfy this pattern, and then filter is applied with predicate R2.b equal to R1.b. So this is just the same that saying that each match where can be sought as a select from. Actually, if we can write another Cypher query looks something like this. But as you can see, this graph pattern looks very much different, because the difference is here compared to our previous query is that in our previous query, right, our we use this match and we specify the graph pattern. But in this case, we don't really do that at all. We're just saying, okay, we want to match 3 nodes and we have our where clause and we want to just return. But you can see the plan actually look very different than the previous picture. So here we can see that actually they perform a directly join. So we have this node by label scan, and then we have this value hash join, and then we have node label scan, then we have this value hash join. But if you run this query inside the Cypher, it will have this warning that says that this query builds a Cartesian product between disconnect patterns. That usually means that even though we are essentially doing the same, so this two query returns exactly identical result. So this query is not a favorable way for Neo4j, even though they are meaning the same thing. So just to give here we do a little bit of case study. So just to give you a concrete sense about what graph or what Neo4j or Cypher query can do, how we can use this. So this is a term project that's done by a student in the same class in spring 2019. The goal is to enable run queries against a large collection of data, around 2.2 million rows gathered from students' workplace. So example query can, for instance, where are all my photos? Or similar scenarios, like we want to query against files stored in S3 bucket, or query against log files collected over time from different services on AWS. So the method here is that we model the data in relational model, and we also model exactly the same data in graph model, and then we compare their performance. So independent of the database, so one is a relational database and the other is a graph database. The raw data comprise a labeled direct essentially they are the same graph, but implemented in different data model. And so the first one is Q1. The first query is that we want to find all the paths of files that match a given file name. So this is actually the SQL query, and this is the graph query. And as you can see, the Cypher query is much shorter than the SQL counterpart. That usually means that easier development and code maintenance. And in terms of performance, from here we can see that in this case, actually, despite it seems that it's always be the case that graph database should be much faster than the relational database, because graph database is purposely built for graph usage scenarios. However, in this case, we can see that actually that's not true. In terms of performance. So for example, in this query, find all txt order limit 1000. Then we can see that Neo4j runs around 600 milliseconds, but Postgres is 10 times faster, with around 60 milliseconds. And here we have this, different that's exactly the same query, but you express them using different kind of like Cypher syntax, and we can see their performance changes very dramatically. So that means that Cypher query still needs some hand tuning to reach stable performance. That means that there are more work to be done in their optimizer to optimize such queries. So at the very end, we just take a look at what exactly SQL PGQ look like. We talked about it at the very beginning of the class. So this is SQL PGQ. As you can see, actually we have this again the SQL here, but we also have this this constraints, and this lives in here. So lives in is here we have this type, and we have constraint, which is kind of like foreign key, a little bit weird. This is actually the native SQL to represent this graph, which is foreign key. But in this case, how we can create property graph. In this case, using SQL, we can just say create property graph, social network. We have our vertex tables, which is city and person. city person here, and then we have our edge table. So instead of saying that we have this, we create a bunch of tables, using separate statements, we can just, compress all of them into one statement. And here, if we want to query it, we can see here we have our select from, but inside from we have this our familiar match clause here, and we have again a little bit almost identical syntax to the Cypher case. So, so the takeaway from this one is that essentially what you learned today, or what you see about Cypher, when you or your experience with Neo4j will generally translate into later on in the future when single PGQ become dominant in the market. So let's summarize what we saw today. So we introduced edge label graph and property graph, and we discussed their difference with each other and with relational model. And we introduced graph query languages. So there are a bunch of them: Sparkle, Gremlin, and Cypher. But they all support some important usage patterns, which are graph pattern matching, path query, and the navigational graph pattern matching. And we demonstrate and practice those usage patterns in Cypher and with Neo4j, and we introduce Cypher query profiling using exactly explain command in Neo4j, and we see some examples. And also do a real world case study on relational model versus graph model. And usually the takeaway message is that graph query is easier to write and maintain, and Neo4j has a long way to go to build a sophisticated optimizer like Postgres. Okay, and that's it for today. So thanks for your attention, and if you have any questions, feel free to post it on the discussion ad forum, or send me an email. Okay, thank you.
Thank you. Have a good day.
And I will post the recording later on the ad discussion.
Thanks.